Term 3, Part 2, Volumes of Revolution, using something called the washers method. If you don't already know what a washer is, washers are used in plumbing, electrical, and so on. This is the Wikipedia page on washers, has this nice picture of washers. Washers typically are made of metal or plastic or rubber, and they'll consist of two circles with the same center, with the inner circle being removed. The third row, I think, are called star washers, and they're not what we're referring to here. But the first two rows are metal washers that are more typically used. And so when we talk about the washers method, we're talking about a shape like the top two rows and the bottom row. So let's go back to our problem 1. The region in the first quadrant, enclosed by the y-axis, the graph of y equals sine x, the graph of y equals cosine x. So we're talking about this region, is rotated about the x-axis. So it's rotated about that to form a solid. Let's have a look at creating this solid. The blue graph is the graph of cosine x. The brown graph is the graph of sine x. And we're going to revolve it about the x-axis. And you can see that the solid form has got this hole in the middle. It comes from the fact that our region that we're revolving isn't flush up against the x-axis. There's a gap between this bit of the curve and the x-axis. So when it revolves, it leaves a whole, an empty space in the middle. I always think that this would look like a dog bowl on its side. So if we go back to that, you can see that one of the cross sections are going to be washers. So, and you can see that the area of the washer varies. That hole in the middle gets bigger depending on the position of the washer. Okay, so let's go back to our notes. All right, the cross-sectional slice will be a washer. And so let's write that into the notes. It's going to be a washer of thickness delta x. And the volume of this is going to be the area of our cross-section times the thickness of it, which is delta x. All right, so the thickness is delta x. I need to know what the cross-sectional area is. And so let's see if we can figure that out. My shaded area is equal to the area of the big circle by itself, which is pi big R squared, and then minus the little circle inside it, which has radius little r, so minus pi little r squared. So our volume of the solid of revolution is going to be the integral of my a of x dx, one of my washer slices. And to get the limits for my definite integral, it's kind of given away on the diagram. I've kind of done the heavy lifting for you. But if you weren't told that the x's go from 0 to pi over 4, it's easy to find. Your points of intersection of your two curves is going to be found by putting sine x equal to cosine x, as those are my two curves. Divide both sides by sine x. Normally we don't divide both sides by an expression involving the variable, but because we can lose a solution, but we actually don't lose our cosine. It doesn't cancel out. It's still sitting there under the sine x as tan x. So tan x is equal to 1. X is pi over 4. And that's how we get the x coordinate of my point of intersection. So my limits go from 0 to pi over 4. Okay, and now we're all set to find our answer. It's the integral from 0 to pi over 4. We said that the area of a cross-section washer is pi big R squared minus pi little r squared, and the thickness is delta x, so it's going to be the integral of this vector x. Factor out my pi and put it outside, and I'm going to get big R squared, and I need to work out what big R squared is. Okay, how do we find big R? Well, let's have a little look. It's going to be the distance from the center of my washer to the outer rim of my washer. Let's do that on my bird's eye view, which is a diagram you'll be working with pretty much. There's my bird's eye view. There's a bit of the washer that's actually in my region. Okay. And so what the center of the washer is going to be, sorry, my center of the washer is here. And let's write down some coordinates. Okay, we're going to, with a washer, the important thing is we're going to mark on 3 coordinates. So the disk, we just had 2, center and the outer, the rim of the disk. Here we're going to mark on the coordinates of the center, the inner rim of the washer, and the outer rim of the washer. So here we go. They all have the same x coordinate. That's a good way of reminding you you're working in x's. All right. The y of the center is 0. The y of the inner rim is sine x. The y of the outer rim is cosine x. So my big R is going to be what? I go from the outer rim to the center. So, and these are vertically above each other, so it's the upper y minus the lower one. So it's cosine x. Little r goes from the inner rim to the center. I can't stress that enough. It's not the distance between the rims, but always to the center. So going back to my volume, it's going to be big R is cosine x, so big R squared is cosine squared x, minus little r is sine x. When I square it, it is sine squared x dx. I could put etc. here, but this is a good place to remind you of a good trig identity, and it is one you're expected to remember from pre-calculus. Remember that if you have cosine of a plus b, that was given by cosine A, cosine B, minus sine A, sine B. Cosine, cosine, minus sine, sine. All right, now what happens when I have cosine A plus A? So in other words, I'm replacing B by A. I'm going to get cosine A, which is cosine squared A, minus, so I'm replacing b by a, that becomes sine squared a. So I have the identity that cosine 2a is cosine squared a minus sine squared a. So my cosine squared x minus sine squared x is 0 to pi over 4 of cosine 2x dx. And just do a little bit more work on this. Oh, we're going to anti-differentiate, so let's get rid of the integral sign and replace that by a square bracket. There we go. I could do this with a u substitution, letting u be 2x, but that's a linear substitution, so it lends itself well to guess and check. What gives me cosine? Differentiating sine, and it has, of course, be sine of 2x. And then there has to be 1/2 to account for the chain rule when we do our guess and check. And the limits are going to go from 0 to pi over 4. And at this point, I can really say etc. Okay, let's just summon up our strategic approach. Notice the cross sections are always perpendicular. They're always perpendicular to the axis of revolution. The center of the washer, like the center of the disk, when we did disk, will lie on the axis of revolution. And always mark on, put that in a cloud because this is so important, 3 points with their coordinates. The center, inner, and outer rims of the washer, remembering to pick the inner and outer rims of the washer where you actually have know the equation. So we picked the inner and outer rims of the washer, with the 3 red dots, as opposed to going with, the inner and outer rims here, because I don't know those equations. I'd have to work to find what they are, and sometimes that can be more complicated. Okay, when the axis of rotation is not an axis, like x or y-axis. Okay, let's do some examples. Actually, example 2 is the same area that is being rotated, but it's rotated about 4 different axes of rotation. So example 2, find the volume of the solid formed by revolving the region bounded by y equals root x. So we're going to do this here on the little diagram. Here we all know this, well familiar graph. Y is root x. The line y equals 2, which is a horizontal line, y equals 2. And x equals 0 is the y-axis. So the region that's going to be rotated is this region. Okay, so let's mark this on our diagram for actually thinking about rotating it. So let's go. The first rotation is about the x-axis. If I allowed myself enough room, yes. Okay, so here's my region. And I'm going to rotate it about the x-axis. Let's do that. It would be really nice if we knew what the points of intersection were, what the coordinates of this point happen to be. So let's quickly find that. Okay, point of intersection. We've got y equals 2, y equals root x. That means 2 is root x. X is going to be 4. So this point has got coordinates 4 and the y is 2. So there we go. All right. And we're going to take this region and revolve it around the x-axis. And actually, we can look and see what happens with that one. Let me see. I'm pretty sure it's here. Yes. Oh, wait a minute. I've got that set up for something else. So we'll just have to do this one by ourselves, I think. Sorry about that. It's going to be very similar, in fact, to the one above, because there's a gap between, this curve and our axis in rotation. It's not flush up against it. When it rotates, there's going to be a space left in the middle. So how do I sketch my solid that I obtain when I do my rotation? Well, it's very similar to what we did with our disks. We do the reflection of my region, okay, in the axis of rotation, And when we do the curves, it's a good strategy to do them as dotted lines. Okay, and so, you know, this is going to be my reflected region. Okay, and then what we get when we do our rotation is that we're going to get washes. I'm going to try and sketch one of these washes. Okay. And let's write that down. We're going to get washes. And the thickness of my washer is going to be delta x, because you can see it's in the x direction, the thickness. And we need, so when it's washers, I know my volume is going to be the integral of pi big R squared minus pi little r squared. My thickness was dx. Okay, and my x's are going to vary between 0. Okay, I'm going to start at 0 and I'm going to finish at 4. So my x's go from 0 to 4 as I take all my washers going from left to right. And it's just a question of figuring out what my big R and my little r happen to be. Okay, remember what the strategy says. We're going to mark on 3 points, the center of my washer, the inner and the outer rim, and I do it where I have the equation. Okay, you know that. Okay, let's write down the coordinates of those 3 points. They all share the same x coordinate. That's a reminder that you're going to be working in x, and it's a y's that are different. The lowest from the center has a y of 0. The inner rim has a y of root x, because that was the curve, y equals root x. And the outer rim has got a y of 2 because it's on the graph of y equals 2. Okay, so let's figure out what big R and little r happen to be. Big R is the distance between what? The outer rim of the washer, there it is, and the center. Okay, 2 vertical points, one above the other. I subtract the y values. It's going to be the upper y, which is 2, minus the inner y, the lower y, which is 0. So big R is 2. Little r is going to be the distance between the inner rim, this point, and the center. It always goes to the center. So the little r is going to be root x, the upper y minus the lower y, which is root x. So we're almost set to go. Factor out the pi. My integral goes from 0 to 4. What is big R? It is 2. So it's 2 squared minus what's little r? Root x squared dx. And so that's what pi integral 0 to 4 of 4 minus x dx. I'm going to write etc. because I know you can do that. Okay, let's do the same thing all over again, but with 3 different axes of rotation. So we're going to draw our graph, y equals root x, y equals 2. Whoops, that's not a regular line. Okay, so there's y equals 2. There's y equals 2. And let's shade in my region. It's always a good idea to shade in your region so you know what you're talking about. We know our points of intersection. This is for 2. And this time I'm going to rotate it about the y-axis. Now, if you look, the region butts up to my axis of rotation. There's no gap left. It's actually flush with it. And so when I rotate around my y-axis, there's no space left, created rather. And here is my reflection. And I don't know if you can see that we have got a, not a washer this time, but a disc. Here is my cross-sectional disc, and we notice that the thickness in this case is delta y. So we've got to be working in y's, okay? And we're back to discs, all right? And with disc, we need to know what the radius is, and it's just one radius, obviously, with a disc, all right? And how do we do that? We mark on these 2 points, the center of the washer and its rim, okay? And we notice they have the same y coordinate. It's the x's that are different. So they have the same y coordinates. We just call that y because it's just any cross section. The center is easy. That's got an x coordinate of 0. The outer is on our given equation, y's root x, but remember we want to work in y's. So we have to take the equation y's root x and rewrite it so it's in terms of x equals. So x is equal to y squared. All right, so the radius of my washer, I've got 2 horizontal points. To find the distance between them, it's the right x minus left x. So it's y squared minus 0, which is y squared. Okay, and we can do our volume now pretty easily. It's going to be the integral of pi r squared dy. Okay, so working in y's. So take and my limits, working with y's, my y's are going to go from 0. So the y starts at 0 and it goes to 2 in this case, 0 to 2. Okay, so I've got to take the pi outside, limit 0 to 2. What is little, it's r squared, and r is y squared. So this is the integral of 0 to of y to the 4th dy, etc. Okay. All right, let's look at the third example. I want to take the same region. So my same region. Ooh, okay, here it is. I'll move it up a little bit. How about that? Okay. And here is my point 4, 2. Let's shade in my region, do that every time, good idea. But this time, instead of rotating it about the x-axis or the y-axis, we're going to rotate it about the vertical line, x equals 4. So let's put in our line x equals 4. All right, okay, and let's put in our line. Ooh, here we go. All right, let's move it over a tad, if I can. Oh, come on. Okay, this is going to torment me. I'll just sketch by hand. Whoops. There we go, got it back. Let's put in our line. Here it is. This is my axis of rotation. X equals 4. So I'm going to rotate the shape about x equals 4. What is it going to look like? All right, I think this is the one that I had set up for us. Here it is. Okay, hopefully you can see it. There is the line, see if I can pull this down a tad. Nope. All right. There's a shaded region. You can't quite see the point of intersection. Let's move over the axis of rotation. The point of intersection is slightly out of the view of the video, but let's just see what happens when we revolve. Okay. You can see that we're creating washes again, and depending on, see there are all my cross sections, they are washes. Unfortunately, the top of intersection is just slightly out of the frame of the picture, but I'm sure you get the general idea. So let's go back and create our other half. Let's see, remember what we do. We reflect our region in the axis of revolution, something like that. And here is what we get when we reflect it. Kind of big on the right hand side, never mind. Let's look at one of our washes. Actually, this is going to drive me crazy if I don't fix it. Okay, that's better. And here is one of our washes, one of our cross-sectional washes. Hopefully you can see it. Okay. All right. So there is our cross-sectional washer. So let's write that down. That's how we're going to attack the problem. It's a washer. And the thickness this time, hopefully you can see it's in the y direction. So the thickness is delta y. So we'll be working in y's. And for washers, we need to know what big R and little r happen to be. And remember what we said. For washers, we mark on 3 points: the center of the washer, the inner rim, and the outer rim. And we mark them on where we know the curve. So I'm not going to do it on the right-hand side, but on the left-hand side, because I know the equation of that inner rim spot. So let's write down what big R is. We do that when we write the coordinates of our points. Notice they all have the same y value. That's a reminder that we're going to be working in terms of y. A little hard to see with this. They have the same y. The x of the center is 4. The inner rim, okay, it's on the graph of y is root x, and we already know that's x is y squared. So it's x is y squared. The outer rim of the washer has an x of 0 because it was on the y-axis. Okay. So big R is what? The distance between the center and the outer rim. So let's identify the center and the outer rim. Here's the center, here's the outer rim. Okay, so I'm going to do the right x minus the left x. Want to be sure we get the signs right. So it's going to be 4 minus 0, which of course is just 4. Little r is going to be the distance again from the center. It's not between the rims. Between the center and the inner rim. So that's going to be given by the center had an x of 4. The inner rim had an x of y squared. So we're ready to go. The rest is just plug and chug. The volume is, it's washers, it's integral, and it's thickness delta y. So it's going to be what happens to the y's. The y's vary between 0 to 2. Okay, the y's vary. If you look at all my washers, They go from 0 to 2. And then it's going to be, it's washer pi big R squared minus pi little r squared dy. Notice I actually don't factor out my pi until after I've kind of gone pi r squared minus pi little r squared, because sometimes people forget about the pi. Now I'm going to factor it out, and then I just plug in big R was 4 squared minus little r was 4 minus y squared dy. And if I were doing this analytically, I need to FOIL out that 4 minus y squared all squared, and etc. Okay, last one, same region. This time we're going to rotate it about the line y equals 2. So let's do that. Here is my graph, y equals root x. Let's do y is 2. This is a graph of y equals 2. Here's my shaded region. Okay, all right. And we're going to actually now rotate it about y equals 2. And notice I'm flush up against my axis of rotation. No space between it. It's not going to be a washer, but you've guessed it's going to be another disk. Okay, here is my reflection in the axis of rotation, and here is a typical cross section, and it's of course going to be a disk. So this is a disk, and the thickness, we are back to thickness delta x, okay? The thickness of this washer is in the x direction, all right? So remember, with a disk, we've just got a radius, just the one radius, and that radius is going to go from the center. You mark on the center, the center of the disk and its rim, and you mark it on in your original region where you know the equation. Okay, let's mark on their equations, and don't skip ever the step of marking on the equations. Trust me on that. They have the same x coordinate. That's a reminder we're working in x's. The y's are different. The rim has got a y of root x. The center has got a y of 2. And so the radius is going to be given by, I've got two vertical points vertically above each other. It's the upper y minus the lower y. Okay, and so my volume is going to be the integral of area of the cross section, which is pi r squared dx, and my x's, this was a 0.42, so, and this is 0, 0. My x's go from, this would be the 0.02. So my x's go from 0 to 4, 0 to 4. Okay, and almost done. It's the integral from 0 to 4. We take our constant multiplier out. It's r squared. What is r? 2 minus root x dx. You FOIL and anti-differentiate, and so on.